So let's say that we know the velocity vector as a function of time is equal to t for the x component and 2t squared for the y component. And let's say that when time is equal to 0, the position vector is 4, 2. Okay, so you can think of what this means is at any time this represents the velocity vector of the object, and when time is equal to 0, these are the coordinates of the object. And here's what we want to do. So first we want to calculate the position as a function of time and the acceleration as a function of time. And then second, we want to calculate the velocity vector and acceleration vector at time equals 1 second. And we want to use those to figure out what can we say about the motion. And so here are the kind of things that, like for example, which way is it moving? Is it speeding up or slowing down? Is it turning? Okay. Okay, well, we have the velocity vector. What do we have to do from this velocity? So this is a vector function. To go from velocity vector as a function of time, how do we get to acceleration as a function of time? Yeah, take the time derivative and, right, time derivative. So acceleration as a function of time is the time derivative of the velocity vector as a function of time. And so to do that, we just take the derivatives of each component. What's dt? So if you're taking the derivative of t with respect to time, it's just 1. If you're taking the derivative with respect to time of 2t squared, that's 4t. Okay. That was just derivatives, so there's no constants of integration. So this is the answer to the acceleration as a function of time. Okay, that one was a little easier than going the direction of integration. What about the position? So that one we have to integrate. With respect to time. So if we integrate t with respect to time, we get 1/2 t squared. And then you also have the constant of integration, so I'll call this C1. And for the y component, we'll integrate this. And so you get 2/3 t cubed. plus a constant of integration that doesn't have anything to do with that one, so we'll call it C2. But we're not done yet because of these constants of integration. So now we have to use the boundary conditions that are given to figure out what those constants are. So the boundary conditions now, we're given that when time is equal to 0, the x component of the position is 4. So 1/2 times 0 squared plus C1 is equal to 4. And in other words, C1 is equal to 4. So the x component of the position as a function of time is 1/2 t squared plus 4. Any questions about that? What this says is when time is equal to 0, px is equal to 4. So we'll put 0 in place of t in the equation and put 4 in place of p. You know, so this equation says px is equal to 1/2 t squared plus c1. So set t equal to 0 and set px equal to 4. And now we'll do it for the y equation. The y equation says set t equal to 0, set py equal to 2. So 2/3 of 0 cubed plus C2 is equal to 2. And so C2 is equal to 2. And so Py as a function of time is 2/3 P cubed plus 2. And so if you put these two together, you get that the position vector as a function of time has Px as an x component. So 1/2 t squared plus 4. And Py is a y component. 2/3 t cubed plus 2. Okay. So now we have functions that represent the position vector, velocity vector, and acceleration vector as functions of time. And now for part B, we want to know, and this is just totally arbitrary. I mean, I could have asked for any time value, and we could have plugged it in and gotten the position, velocity, and acceleration. But I asked for position, velocity, and acceleration when time is equal to 1 second. Okay, so what do we get for these? Well, the position vector is 1/2 times 1 squared plus 4. So that's 1/2 plus 4, so 4.5. Plug in 1 in the y component, you get 2/3 times 1 plus 2, so that's 2.6 repeating. So what that means is at that instant, the object is there, you know, whatever, you plot that point. That's the location of the object. at time equals 1 second. Now the velocity at time equal 1. Okay, so now let's plug 1 second in for our velocity function. That was what was given in the problem. Plug in 1 second for the x component, you get 1. Plug in 1 second for the y component, you get 2. So the velocity is 1, 2. Right? Yeah. By the way, this one would have units of, I don't know if I gave any units, but it has to have units of length. In most cases in this class, that would be meters. This would be units of meters per second or some kind of length per time. Okay, so what does this mean? Well, this velocity, if you put the tail of this vector at the origin, you can plot this. It says you go over 2, up 1, and that's the head of the vector if its tail is at the origin. So this is the direction that the object is moving. Well, and the magnitude gives you the speed. Okay. Over, yes. It sure would. Over 1, up 2. Okay. So, in other words, how that relates to the origin doesn't matter, but that is the direction that it's moving at that instant. And the magnitude is the speed at that instant. And then the acceleration vector at time equals 1 second. There's no t in the x, so that just stays 1. Plug in 1 for t here, and you get a vector 1, 4 for the acceleration. Get a sense of the direction here. We'll go over 1, up 4. So it's steeper than the velocity vector. And now what can we say about, what can we say about the direction it's moving, whether it's speeding up or slowing down, and whether it's turning, and if it is, which way is it turning? Okay. Well, the velocity vector is this way, right? So that's the direction it's going. The acceleration vector is this way. Okay, so this is the velocity vector. This is the acceleration vector. That's what we figured out. Okay. And to figure out whether it's speeding up or slowing down and which way it's turning, we're going to break up that acceleration into 2 components. Okay. One that's parallel to the velocity vector, and one that's perpendicular to the velocity vector. Okay. These are 90 degrees from each other. So based on that, is A parallel in the same direction of the velocity or the opposite direction? Same, so is it speeding up or slowing down? Speeding up. And then A parallel is that way. which means that it's turning that way, not that way. Okay.